Okay, so this particular set of slides is linked to the overview of the different separation processes that we will all also discuss this semester. So in this slide, we will be talking about the phase equilibria. So mass transfer, and that is the transfer of one component from one phase to another, ceases or stops when an equilibrium between the two phases is reached. This is the primary premise or principle that is used when we transfer a particular component from one phase to another in the different separation processes that we're going to discuss. So the rate of mass transfer in here is directly proportional to the driving force, which is a departure from the equilibrium condition. So how fast will the component be transferred to a different phase coming from another will be dependent on this driving force. So let's look into this particular driving force. So for driving forces, so when we speak of driving force in mass transfer, this could be based on the differences in vapor pressure or solubility or even diffusivity. Now, it could also be, as the common thing is, the concentration difference or difference in the activity of the species. Now, when it's a pure mechanical separation of components in a mixture, it would be based on, referring to the driving forces, in the density difference or particle size. Now, this would be our basis in some of the membrane separation processes at the end of the course. Then if it's the driving forces for heat transfer, which were done already last semester, that would be the temperature difference or temperature gradient. Now, in phase equilibria, to be able to evaluate the rate of mass transfer, the driving force has to be accurately determined, which in turn rely on the equilibria or the state of equilibrium between the phases. So we won't be able to accurately determine the rate of mass transfer or even just the recovery of a component from one phase to another if this particular driving force was not accurately determined or even established. In nearly all situations, two phases are involved except when we have two solid phases. So in here, when we speak of separation processes, we normally have two phases. Now, the controlling variables are the intensive properties, temperature, pressure, and concentration. So this controls the rate in which equilibrium is reached, or even the rate in which the transfer of mass is accomplished. Now, the equilibrium data, where we are going to base the computations in most of the problems that we will be tackling, will be either in the form of, or shown in the form of tables, the relationships that is, equations, or graphs. So if it's in the form of tables, it will be something like this. And last semester in your gas absorption, you already saw this table, if I'm not mistaken. So in this table, this is, by the way, only true for the benzene-toluene system. So for equilibrium relationship between systems, we have a unique set of tables for each system. So one system's table may not be, or is actually totally different from another system's table. The system that we have here is the benzene-toluene system, and this is an ideal system. And what you have here in the first two columns will just simply be the temperature in which the vapor pressure and the mole fraction of benzene in the liquid and in the gas phase will be based into. So what I'm trying to say is, for you to be able to know the vapor pressure of benzene or toluene, or for you to know the mole fraction of benzene in the liquid phase, and that is XA, or the mole fraction of benzene in the gas phase, that is YA, you need temperature as a basis. And then all you have to do is read the corresponding data that you would want from this particular table. Okay, this is good for benzene and toluene. Though this table does not have all the properties having linear relationship, then we can simply approximate. If it's really difficult, or it would require us a lengthy procedure of having to really draw the graph of the vapor pressure against temperature for one particular component, then another component, and even the graph of XA and YA based on temperature. As, as it is, the relationships here again are not linear, but you can approximate by simply interpolating or extrapolating on the basis of the temperatures that you have in the first two columns, so that you won't have to graph the actual curve and then actually read from that same graph that you have drawn the value for vapor pressure or mole fraction in the liquid and the vapor phases. So the equilibrium relationship in this case as shown is in the form of a table. Now, it could also be expressed in terms of an equation. So again, last semester, for you who have taken the heat and mass transfer, you already encountered Rayold's law, and you know already that this is only applicable for ideal solutions. So in here, the law states that the partial pressure of A in the gas phase is actually directly proportional to its mole fraction in the liquid phase, and that's your XA. This P sub A is a constant which is based upon the temperature because this is the vapor pressure of pure A. Okay, so Rayold's law gives you the relationship between XA and PA. But again, this is only true for ideal systems. So if your system is not ideal, you have an alternative equation to use, and that is your Henry's law. So it's comparable to Rayold's law. The only difference is the constant here. So in Rayold's law, you have here the pure vapor pressure of A, but in Henry's law, you have the Henry's constant. Where are you going to get this Henry's constant? You can get this in the appendices of our reference books, or you can find this in the handbook as well for a particular system, again, based on the temperature. So Henry's law is dependent on the temperature. Let's say, for example, for SO2 air mixture, you have a different H. For CO2 air mixture, you have a different H. So it's dependent on, but nonetheless, both are dependent on the temperature. Now, from this original Henry's law, you can get a relationship of YA and XA. All you have to do is divide this equation by the total pressure of your system. Most of the time, this is 1 atmosphere. Then your partial pressure divided by the total pressure on the left side will be converted to your vapor pressure of A, or rather, sorry, the mole fraction of A in the gas phase, not the vapor pressure, the mole fraction of A in the gas phase. And in here, the H constant, when divided by the total pressure, will simply be H prime, a constant which will have an added unit in the denominator based on the unit of the total pressure, which was used as your divisor. Now, by the way, in these two formulas, Rayold's law and Henry's law, we apply these two liquid gas systems or gas liquid systems. Now, this one, the K-factor distribution coefficient, or simply the distribution coefficient, this is used in extraction or in liquid-liquid extraction. Now, this one is the ratio of the mole fraction in the vapor and the liquid phases at equilibrium. So meaning this mole fraction that you're going to measure should be measured, the ratio of these two mole fractions, that is, should be measured at the state of equilibrium. This would now give you the distribution coefficient of your system. Now, if your system is ideal and Dalton's law hold, we can also replace the Y and the X here by the pure vapor pressure and the total pressure of the system. The pure vapor pressure of I over rather the total pressure of your system. That's for your distribution coefficient that is often used or encountered in liquid-liquid extraction. You will know how to use it when we're on the topic already of liquid-liquid extraction. Now, you can have this also in terms of the ratio of the mole fraction in the gas phase and in the liquid phase in here. So you have mole fraction of component I in the gas phase divided by mole fraction in the liquid phase in terms of its ratio of another component, and this is J. In this case, you are determining already the system's relative volatility. Again, this is for an ideal system only. So if Rayleigh law holds, then the ratio of the k factors of your components in a two-component system, I and j respectively, will be this one. The ratio of the two k factors, sorry, excuse me, is equal to the relative volatility of your system. So K factors, take note, are strongly temperature dependent in the same way that pure vapor pressures are temperature dependent. But relative values of K, when we speak of a two-component system, may only change moderately. So we know that if we change the temperature, if the distribution coefficient of one component, let's say I, changes, correspondingly J will also change. So if we're going to look at it on a general sense, the change in the ratio of the two, which is equated to your relative volatility, the deviation will not be much. As stated here, the change is only moderate. Okay, so but again, this is only for an ideal system. Now, for most operations, however, and for the separation processes that we will be discussing, the pertinent equilibrium relationships are shown graphically. So for those who were able to attend the orientation, I have shown to you the CMO. We know for one that the board exam is purely analytical, mathematical. You use formulas and empirical they may be. But nonetheless, the CMO doesn't want you to limit your understanding only on the analytical approach. And as such, I have shown to you that the CMO dictates that even the graphical techniques that are used should be discussed to you. Okay, so we will also discuss that, but we will not really give so much time on that. Now, another way of expressing equilibrium is in the form of graphs, and this is often the case. So you have here the relationship of the mole fraction of, let's say, species A in the liquid phase with its relationship with the mole fraction of A in the vapor phase or in the gas phase. So most of the time, this is the kind of equilibrium relationship that we get data or that we are using in our problems and separation processes. Although, of course, Rayleigh's law and Henry's law is often used as well. Now, as for basis for phase equilibrium, we have the phase rule. In here, the variance, F, or also known as the number of degrees of freedom, is equated to C minus P plus 2. The C being C, so represents the components present in your system, and P, the number of phases in your system, and this is a constant 2. So that's the basis for phase equilibria. And the degrees of freedom, or the F that you are seeing here, variance, this represents the number of intensive independent variables. Independent intensive variables, most of the time, these are temperature, pressure, and concentration that must be fixed to define the equilibrium state of the system. This particular variables has to be defined, it means by the problem. That way, the problem could be solved. Otherwise, it's only two ways, only two things might happen. The problem cannot be really solved, or the problem may have several solutions, not just one. So it's stated in here in the next bullet. So if fewer than F variables are fixed, an infinite number of states fits the assumption. If it's an infinite number of states that would fit a particular assumption, it's impossible for you to come up with a one, shall I say, valid solution, because it's all assumption. And those particular assumptions are infinite in number. Now, that is if your intensive variables that were fixed is fewer than what is solved using the degrees of freedom formula. If the F that was given, or the number of variables that was fixed in the problem, is too many, the system is also over-specified. And as such, it may have, shall I say, if it's in the case of algebra, you have more equations than the number of unknowns, then you will have several solutions as well in that case. So to eliminate the problem of having to make infinite number of assumptions and to make our system have several solutions, we want as much as possible, or the problem as much as possible as given Unless otherwise, it's the teacher who makes the problem should specify the equal number of intensive independent variables. That way, the problem could be solved. Now, for a two-phase system, and that's in our case, because we will not discuss anymore multi-component systems, variance is always equal to 2, which is also equal to the number of components of your system. Most of the time, since it's a two-component system, do you have two components? If, for example, the pressure is fixed, or the pressure is already given in the problem, the liquid phase concentration can be changed independently. Or meaning, if I have a problem and I want to modify it for several sets, I need to fix the pressure, I just change the concentration. Then, the gas phase composition and temperature can be determined in that case. So, it still could be solved. It can still be solved if I vary the concentration and then the remaining unknown requirement in the problem, let's say, for example, is composition and temperature, it could still be determined in that case. Now, to read more on this or to complement what I've discussed here regarding variance, you can read on McCabe and even John Copley's the concept of variance on the topic gas absorption, distillation, and even extraction or liquid extraction. So we have here the sample problem of CO2 in air. So this is your CO2 in air, meaning it's a CO2 air mixture having a total pressure of 1.1333 times 10 raised to 5 Pascal. So the gas phase is in equilibrium with the water solution at the temperature of 303 Kelvin. What is the value of XA of CO2 in equilibrium with the solution? So I will have to share, we will have to solve for this, although I'm sure this is still fresh to your memory. We have partly tackled this last semester. So for that particular system, we need the, like to go back to that, we need the partial pressure of CO2 and the total pressure of the system. So this is 1.333 and this one is 1.133. This is 4 and this is 5. Okay. I think these are the only information that we can work on. So in terms of the given, the partial pressure, let's say CO2 is component A, and that would be 1.333 times 10 raised to 4 Pascal. And the total pressure of your system is 1.1333, but this time it's times 10 raised to 5 Pascal. And this is at a condition at a temperature of 303 Kelvin. I think these are the only two informations that's stated in the problem. The partial pressure of CO2 and the total pressure of the system. And then it's stated that your gas phase is in equilibrium with the liquid phase, that is at 303. So you are to find the value of XA. Now, if you're going to get the Henry's law constant from the appendix in John Copley's, so you can go to that particular page in here, that would be 0.186 times 10 raised to 4. So take note of the unit, it's ATM per mole fraction. So then we will have to add this particular constant, the Henry's constant. Wait, class, I forgot. So that would be 0.186. So you have your Henry's constant, which is 0.186 times 10 raised to 4. This is ATM per mole fraction. So take note, it was really stated here. I'd like to go back. The Henry's law is dependent on the temperature. So you need the temperature to be stated in the problem. That way you can get the Henry's constant. So you have this particular value. I think that's For this problem, we are to find the XA. So your required information is the XA. And since actually, if it's not given in the problem, you are to look for this one. And since our system, the CO2 air system, is not an ideal system, you are a lot safer with Henry's law. Then that would be partial pressure is equal to the Henry's constant times the mole fraction of A in the liquid phase. Now, XA then would be your partial pressure divided by the Henry's law constant. That's it. So your partial pressure, which is 1.333 times 10 raised to 4 Pascal, you divide by Henry's constant, which is 0.186 times 10 raised to 4. This is atm per mole fraction. The units for pressure does not agree, so there's a need for you to convert. So we know that there's 101.325 Pascal for every 1 atm. So we get to cancel this, and we get to cancel the unit for the unit atm. Now you have the answer for the mole fraction of A in the liquid phase. That's it. If you use Henry's law, there's no need for you to convert this to YA, because anyway, your Henry's constant is already given in the problem. So you can simply use the, here am I, eraser. Di naman ko ni kasulat karon. Anyway, oh my. I'm afraid of this eraser because it doesn't allow me to write. Here doing. I don't find. Oh, that's it. XA is, what's the value for XA? So if you're going to solve for this, XA value 4 divided by 101.325 divided by 0.186 exponent 4, that would be very small. That would be, oh, how do I go back? Let me write. I should have done undo. 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 Nonetheless, class, the answer would be 7.07 times 10 raised to negative 5 for the XA. A very simple illustration of how we can use Henry's law in determining the mole fraction of CO2 in the water phase or in the liquid phase. Okay, now we go to a different problem. Oh, where did I close that one? This one, you're given still CO2, and you're given the concentration of CO2 in water in terms of mass, 0.9 times 10 raised to negative 4 kilogram CO2 per kilogram water. So you have to be very careful with the concentrations, by the way, that are provided in the problem. So using Henry's law constant, what partial pressure of CO2 must be kept in the gas phase to keep the CO2 from vaporizing from the aqueous solution? So what would be the partial pressure of CO2? That way it won't vaporize from the aqueous solution. If you're going to look at it intently, the only thing that is given here is the concentration of CO2 in water, and it's given in the form of mass ratio. Look at it. Kilogram CO2 per kilogram water. And you are asked to find the P sub A. In this case, let me just check. This is also CO2, so we can use the same Henry's constant because the problem here is also at 303 Kelvin. So we will now go to our board and find the required information. So for the second problem, it's still CO2. We're talking about CO2. So the concentration of CO2 is equal to, let me check. So it's 0.9 times 10 raised to negative 4. So you have here 0.9 times 10 raised to negative 4. This is kilogram CO2 per kilogram water. This is at a temperature of 303 Kelvin. Okay, this is the concentration of CO2. That's it. And you are required to determine the partial pressure of CO2. Then the problem in itself dictates already that you are to use Henry's law. So you will have partial pressure being equal to the Henry's constant times the mole fraction of CO2 in the liquid phase. So it's more straightforward than the other one, although we will have to do some conversion. In terms of the Henry's constant, we will use the Henry's constant that we used there. So 0.186 times 10 raised to 4, excuse me, Pascal. Sorry, this is, hindi na ako mag-erase because I don't know how to go back to the pen. Atmosphere, I think, per mole fraction. And you are to, supposed to be, you are to multiply it with the mole fraction of A. So there's a need for us to convert in terms of the concentration that we're provided. So let's have another slide here. So the concentration, the mass concentration is 0.9 kilograms. Oh, I think there's an exponent times 10 raised to negative 4. I just place it here. Times 10 raised to negative 4. And this is CO2. And this is kilograms water. If we will convert this to mole ratio, you need, of course, the molecular weights, right? So for CO2, that would be 12 for carbon and 32 for oxygen. So that would be 44. So this would be 44 kilogram CO2 per kilomole CO2. That way we can have this canceled. Now, if it's water, that would be 18 kilograms water or H2O per kilomole water. Now we get to cancel the kilogram water. So from mole, rather from mass ratio, I have converted to mole ratio. So mole ratio. So all you have to do is do the maths here. So you have a 0.9 times 10 raised to negative 4. We multiply it by 18 and we divide it by 44. So you'll have an answer of, in here, 3.68 times 10 raised to negative 5. Your unit would be kilomole CO2 per kilomole water. I want the mole fraction. I'm sorry for my doctor handwriting. So this means that you have, for every 1 mole of water, this much of mole of CO2. So if this is converted to mole fraction, you will simply have 3.68 times 10 raised to negative 5 kilomole CO2 divided by 1 for the kilomole of water plus 3.68 times 10 raised to negative 5 for that of CO2. So this would be now kilomole CO2 plus water. So you will have, actually the answer will not vary much. Let's see. So this one, we divide by the answer plus 1. So your answer would be, as I said, it's 3.682 times 10 raised to negative 5. Did not change that much. But now you have the mole fraction. So you can go back here and substitute the corresponding mole fraction. So we'll have here 0.186 times 10 raised to 4. Okay. And we multiply that to the XA that we have here on the next slide, 3682 times 10 raised to negative 5. So 3.682 times 10 raised to negative 5. This would be now the partial pressure in terms of the unit atmosphere, because our Henry's constant of 0.186 is in atmosphere per mole fraction. Okay? So you have times 0.186, exponent 4. So you have 0.0685 ATM.